Okay, yeah, thanks, Bowen, for the introduction, and I'm very glad to have this opportunity to talk about my recent research. And yeah, so the idea is basically we're extending the stability and the safety analysis to data-driven verification, and especially we want to use these type of techniques for unknown systems. And by using the words to words, because we're really just working on stability issue and not just for safety. And by the end of this talk, I'm going to give a direction how to connect with the stability and the safety verification together. So okay, so long story short, and we have the building block specification for nonlinear systems and like stability and safety, and we want to verify if the system satisfy those properties, and they're great mathematical elegance, due to the Lyapunov function theory. And of course, for a control system, we want to find out the optimal stabilization controllers, and we can solve this HAB equation. But eventually it's going to be a very big challenge because for a high dimensional system, we have a very hard time constructing these Lyapunov functions, especially for computing, not just for a known system, but not to mention for unknown system, it's going to be more challenging, right? So the question is, the traditional method cannot really solve the problem because the system is quite complex. Not to mention, there's some uncertainties involved in it. And just not just for engineers, but even for theoretical physicists, they had hard time to understand the uncertainty and unknown system, etc. And so it's a very interesting story that the last year's physics, a Nobel Prize in physics, was given to these two godfathers of machine learning. So it's like we're embracing the new world, and we have to embrace a little bit of artificial neural networks to deal with this traditional mathematical science. So on the other hand, and it is not quite. So the data science cannot solve everything, right? And because we still have the traditional trifecta of scientific research based on the theoretical derivation and the experiments and computational numerics and etc. And the data science is pretty much like a new area for us to explore. And many of the researchers are focusing purely on this data science. But for control engineers, control theorists, and we're mostly dealing with the ODEs and the PDEs and etc. And every mathematical elegance lies in this middle part, the central part, the theoretical derivation. So in the end, even though we're embracing the data science, we still have to do more or less a little bit model-based analysis starting from here to bridge the gap between this data science and the theoretical derivation. So that's my research vision. And next is how to build this bridge this gap, and because because neural network is basically approximator, right? And I just quote here by a great mathematician Terence Tao, who gave a talk last summer at Oxford. I totally agree with one of his opinion, right? And the AI currently basically is a guessing machine. So we use the AI tools to approximate some quantities, right? But it's hardly to say that they're 100% reliable. And especially we want to use neural network controllers or maybe some other quantities to use them in the safety critical engineering, right? And we don't want them to be unreliable. And so now we have many challenging issues, and we want to solve some equations and to use the neural network to verify if they satisfy some criteria. So here is the big vision of what it is, and we want to investigate if the neural network can solve the problem that we cannot solve the past few decades for the system and control theory. Right, so here comes the main material of this talk, and we start from the very fundamental property of the nonlinear system stability analysis, and then we construct the Lyapunov functions using the PDE characterization and see how much improvement using this method. And then we jump to quickly of the control problems, and then eventually I'm going to talk about something about how to construct the Lyapunov functions for unknown systems so that we can verify stability issue. Right. So just a quick recap of the preliminaries. Say that we have a nonlinear system and it's very standard, and we have a locally elliptic function, vector field F, and then we denote the initial condition like this and the solution by this phi t. And we want to verify if the system, if locally there is the equilibrium point satisfied is asymptotic stability, right? And of course, we can simply assume that this equilibrium point is just the origin, and for simplicity. And another related concept is the domain of attraction. Is just a set of initial condition, so that every solution starting from this initial condition can converge to zero. And we want to, of course, capture as much as the part of this domain of attraction. So there is a very traditional way of doing that. That is called the Lyapunov theory, which says the asymptotic stability of the equilibrium point is exactly equivalent to the existence of some smooth function defined on some open domain, so that this function is positive definite. And most importantly is, the lead derivative along the path is always negative. So it's like this Lyapunov function is like an energy function, right? And we check the evolution of this energy functions along the, with respect to time is always decaying. So that if we observe the energy is decaying over the time, we can say that the system is asymptotic stable. And another related concept is the region of attraction, which is a subset of a domain of attraction. And we, of course, we want to capture as much as this subset, so that we don't have a conservative estimation of the range, so that the system can be verified to satisfy this stability, right? So speaking of this, once we can find out this function is, the target is just to construct this type of smooth function and try to enlarge the estimation of this domain of attraction, right? So it's rather very challenging, and and this theorem exists for almost 120 years, and people still are still struggle to construct this type of Lyapunov function. And previously we have the linearization, and based on this quadratic function, and we solve this AQR equation, and we can come up with the construction of this quadratic type of Lyapunov function. And of course, for polynomial system, there is a benchmark tool called the sum of square, and this tool works pretty well. But the problem is that it's based on this interior expanding, so that by gradually expanding this estimation of the region of attraction, and the sum of square method just do it from the local area, and eventually it's going to be very conservative estimation of the region of attraction, right? So same issue for if we try to use this neural network as the onset to satisfy the criteria provided by this Lyapunov function. And this is just trying to say that we want to make this V to be positive definite, and this part is trying to penalize whatever positive for the lead derivative. And so the results still are not pretty good, because they're basically trying to fit the partial differential inequality, right? And there are infinite many solutions of that, and we don't know which one is the best, right? So based on this issue, and we have a new method, which is not new, but we just recap this PDE characterization of the Lyapunov function, right? So instead of solving this partial differential inequality, we have this type of equation, right? And so, for example, we can set this omega to be positive definite and satisfy some other extra conditions. And we want to construct this function like this. And if this v is infinite, if this integration is diverging, we just set this v to be infinite. Otherwise, we just have a finite v. And we can check the basic properties of this v, which is pretty nice, right? And so the first one is saying, okay, when this v is finite, the domain is actually exactly equal to this domain of attraction, which is the largest domain that we can satisfy this stability, right? And when this x is approaching the boundary of the region of attraction, this v is going to infinity. And of course, we check the lead derivative along the path, which is negative, positive. And so this is the Lyapunov function, right? But we call this a maximal Lyapunov function because the domain of this v is exactly equal to the region of attraction. So it's like we can solve this equation and everything's done. But we observe this v can have a property that when this point is on the boundary and the v is going to infinity. So this is not quite friendly for data-driven computation, right? And this Zubov theorem says we can convert this Lyapunov equation into some other form so that this w, the solution is only have the domain from only have the range from 0 to 1. And especially, we skip the middle part, but we can say that this w can satisfy this 5, right? And it's basically like we transfer the v to this w, and the range, is transferred from from 0 to infinity to 0 to 1. And so there is a nice form, and which is called the Kruskov transformation, and it's basically gave us the connection between this v and w, right? Basically, we penalize every very large value of v to nearly 0, and we send this w to 1. And of course, when this x is approaching the boundary, this w is getting close to 1, and so that's how the boundedness of this type of equation. So instead of solving a Lyapunov equation, we can solve this Zubov equation, like equation 5. So it's not really easy to solve that because the existence and the uniqueness of the solution have to satisfy some other conditions. For example, the viscosity property, and it has to be bounded and etc. We have also some other estimation based on the observing some absolute continuous function based on the residual value and the residual value of the boundary. So when we can observe the c term to converge to 0, we can say that there is an approximation of this w converging to this real solution uniformly, right? And this is the convergence result. And based on this guidance, we come up with the designing of this neural network, especially we redesign this loss function, right? And there are many information included in it. We want to penalize the PDE loss, which is pretty standard. Of course, the boundary loss is also standard. The data loss, capture some extra conditions like we have did in here, right? The unique bounded viscosity solution, and everything is included in this part, which is quite abstract. But I just skip here and saying that, okay, we have to make sure that the designing of the neural network has to satisfy the physics of the provided by the partial differential equation in equation 6. And of course, eventually, because everything converges uniformly, but we have to verify if the derivative can satisfy the property and everywhere. So this is a quite difficult issue, and we do this formal verification, which is saying that when we have this neural network solution of W, and we want to verify if at the local we want to verify if we can use this WB to be as the Lyapunov function, right? So the first step is to, do this local linearization, and we can, solve the traditional equivalent equation and come up with this quadratic form of Lyapunov function, and so that everything encoded by this small region is guaranteed to, have this convergence result. And then the next step is to say that using this W, we can verify if the solution can, eventually reach the first part of the, the neighborhood, which can be guaranteed to satisfy this stability, right? So here are some numerical examples. As this red circle is solved by the linear equation, and within this part, we can be 100% sure that everything is stable, asymptotically is stable to converge to the origin. And so there is a dotted line here, which is the approximation of the boundary of the domain of traction using the new method, which is pretty much close to the true solution, right? And next, we have some non-polynomial system, right? And we compare the new result to the SO sum of square result. And so this green dot is the result returned to us by the sum of square. And it's a local estimation of the region of traction, which is pretty conservative. But the new method said, okay, by solving the equation, solving the PDE, we can have the result pretty much the same as the, the true region of traction subtracted to this small area. And we can solve the PDE by higher dimensional space, and everything is outperforming the traditional sum of square methods. And of course, we extend this type of, PDE solving using the physics informed neural network to the stabilizers to solve this optimal stabilizing controller, right? So we have a different setting because, the control comes into the equation. And we want to solve this optimal control to reduce to minimize this J value function. And it's equivalent to solve this HAB equation, which is pretty difficult because it's nonlinear, right? And our method is to use the policy iteration, and by starting with some initial controller, we can solve this 20, which is linear equation instead of a nonlinear equation here. And then we update the policy, by assigning a new value based on this right-hand side to the left-hand side, and then we iterate this process until we observe this convergence. So, so previously, the convergence result just restricted to, the assumption that the F and G of the system is continuously differentiable, right? But it's quite restrictive, and the convergence result just, focus on the, the topology of the continuously differentiable solutions. But now we have extended to the viscosity solution, which is just Lipschitz continuous. And then we designed the new method like the PIN-PI and the extreme learning machine PI approximation using a similar idea of the previous case, solving the Zubov equation using the neural network. So we have the pretty much similar analysis to say that, okay, this convergence makes sense. And, with the observation of, the convergence of the neural network to the solution, we can guarantee that the limit is pretty much a good approximator of the solution. So here's a quick comparison of the, the new method to the previous benchmark to like a successive Galerkin method, and the most recent popular method of, reinforcement learning algorithms. And as you can see, the result is pretty good, and we have, the very stable calculation of the cost function, which is finite, and the other method can drift out to the infinity very quickly. And of course, we test the controller to the, high dimensional system like 2D and 3D quadrilateral UAVs. And the controller can, make the system stabilize at the designated point. So that's for known system. And now we have some we can take some inspiration of solving PDEs to construct the Lyapunov functions for unknown system, right? And so I'll just begin with some, previous methods. The first one is the very typical Koopman operator method. So what it is like, because we have a possible nonlinear dynamical system, right? The F is a nonlinear vector field, but using the Koopman operator, we can convert the evolution of the ODE solution to linear operator. Right here, the definition of a Koopman operator is for any test function H acting on the solution, right? And so this Koopman operator is linear. And a very related concept is the generator, which is defined by this time differential of this Koopman operator. And so we want to learn this Koopman operator because there are many good properties, and especially this generator, if we focus on the continuously differentiable test functions, the form of the generator acting on this H is just the Lie derivative along the path. So it's pretty much similar to the definition of a Lyapunov function, right? And we have other properties. For example, after learning this Koopman operator of using the data, we can get the eigenfunctions and of course the eigenvalue. And we want to find out every eigenfunction whose the real part of the eigenvalue is negative. And then we come up with, we can use this type of, onsites, which is quadratic, to be as the Lyapunov candidates, right? Because if we take the derivative along the path, and it's going to be negative because we want this phi I to have an eigenvalue to be negative. And then we take the linear combination of all of those, and we hope this 27 is the Lyapunov candidate. So this method is pretty interesting, but it's also not desirable because we have tested on many numerical examples, and whatever we have is a very conservative estimation of the boundary of domain abstraction, right? Partly because still we're trying to fit in this partial differential inequality, and the other is we're trying to use this pretty discrete space to to span the whole Lyapunov candidate space, which is not going to be dense enough. So here is the new method that I proposed, like 2 years ago, which is called the Zubov-Koopman operator. So what it is inspired by this Zubov equation, which is on the left-hand side, right? And we have taken a further step of transformation to the right-hand side, and it's pretty intuitive because the U is just equal to 1 minus V, 1 minus W. And so solving either one of this equation is equivalent to get another one, right? And just the solution of this equation is based on this Kruskov transformation. And we start with the constructing this V. And for every finite V, we just transform this V to the exponential form, and we have this UH. So it's like for any test function, we can construct this 28. And this 28 is readily be the viscosity solution of this equation, which is just the same, right? And we just use a different H here. And most importantly, if the H is the identity function, everything is the same as the U, and the 1 minus U is the original solution of the, the Zubov equation, right? And we can do another transformation by taking the logarithm, and this V is the unique solution of this Lyapunov equation, right? So one thing to remark is that this V is probably not a Lyapunov function because it may not be derivative, but once it's differentiable, this V can be a Lyapunov function. But when we solve this using the traditional method, like using Payne, we don't know much about the differentiability of this V. So even though we solve it, we don't know if it's really a Lyapunov function. But there's a good theory that says, okay, for every Lipschitz continuous Lyapunov function, we can have a pretty good smooth approximator of that, which can be a Lyapunov function. So this is given by the paper by the Professor Grun, and back to 20 years ago. This is a type of which is 2001. And we're gonna see how to use the Zubov-Koopman operator to approximate this V so that this V can be smooth and can be readily be a Lyapunov function, right? So here is the proposal and the definition of the Zubov-Koopman operator. So by just observing this form, and you can see that 29 and 30 are pretty much similar to the previous page, except we have replaced every infinity to this t, right? And the t here. And previously we just have the infinity here. And so what it means is like this t, this Zubov-Koopman operator t, map from the H, which is the initial condition, like some PDE to some other solution domain, right? And we call it the Zubov-Koopman because we have observed that this part is just the definition of Koopman operator. And the first part is a contraction mapping if we can have a finite value of this V, right? So there are many good properties of this Zubov-Koopman operator, right? For example, it's still is a semigroup, right? Just like the Koopman operator, and it just seems like to solve some time varying PDE. And the second one just say, okay, indeed solve this Cauchy problem with the initial condition of the PDE of H, right? We just set H to be the initial condition of the PDE, and we want this TH to solve this 31. So this part just to say, okay, the 31 can only have one unique solution, which is just the TH, right? And of course, it doesn't have to be continuously differentiable. It can be extended to a viscosity solution, and I just skip this part. But you know, just based on this observation, you can see that the right-hand side of 31, and maybe just to ring a bell to you, like it's pretty much similar to the last page here, right? It's just like we're sending the right-hand side of the equation to 0. We can have, you know, the thing is just exactly the same as the Zubov-dual equation. And it's just saying that when we have the solution of the Zubov-dual equation is just the steady point of this time varying PDE, right? It's like we're extending this t to infinity and everything is okay. And we can use the solution of t infinity h to be as the solution, right? And the last part is even more interesting because we have proof that the UH is just the eigenfunction of this t with the eigenvalue 1. So so it's intuitive that we can just start by learn this TT small t by using some data-driven methods. And once we have this, you know, eigenvalue 1, we can say that the corresponding eigenfunction may be the solution of the Zubov equation. But actually, it's not, because we want this UH to be a real valued function, right? And when we learn this Koopman operator, we may have some complex valued eigenvector or eigenfunction, and eventually the, you know, the function that, you know, corresponds to this real value, to this eigenvalue with 1 may not be the real function that we want to have. So we propose another type of approximation using this time series approximation. And because we have this nice property, just say, okay, no matter what, and this t by setting the small t to infinity, we can have this convergence uniformly to the real solution of the Zubov equation. And then, you know, it's simply just say, okay, we can pick a very small time interval, right? And we just learn this capital T. And then after learning this, we iterate it. And, you know, we iterated this K, and acting this iteration on this identity function, we can get the U, right? And to learn this T delta, we can use the, you know, very traditional operator learning method. It's a similar story at the Koopman operator learning, right? And basically they're the same, except that we have this contraction mapping in front of the Koopman operator. right? And everything can be observed with this uniform convergence based on this equation 35. And here comes the real convergence result, right? And the first part is saying, okay, this TH can solve is the unique viscosity solution to the time varying PDE. And the second part is a little bit long, but I just the main idea is saying, okay, if we can approximate this TH by some approximator, and we have the residue to be bounded, and when this bounded residual term can converge uniformly to zero, we can have this approximator uniformly converge to this small th, which is pretty obvious. And the third part is saying, okay, if we want to use this transformation to construct the Lyapunov function, we have to be very careful about the extra convergence of the Lipschitz constants of this small residual term, because we have observed that there is a part, if we take the logarithm, we take the derivative, and this small term is going to be mainly just come from the derivative of the small term here, and the inner product with the f. So even though this theta term converge uniformly to zero, we don't know if the derivative also is going to be convergent, especially if we want to approximate this function by using some Fourier basis, for example, and if we have a high frequency of oscillation, and this term is not likely to converge, right? And eventually we cannot use the transformation result to be as the Lyapunov function. So this is what it is. And so here is a quick summary of the approximation theory. So we start from the Zubov dual equation, and we learn this Zubov Koopman operator defining here. And of course, we do some truncation because of the domain, right? It's probably open, and we want it to be compact. And then we have a good approximation of using the compact operator to be, approximate this T as well. And the right-hand side is to, what we have talked about, using the time theory approximation to be as, to iterate it. And then we act on some function so that eventually this U is what we want to approximate. And then, the rest of the part is, the same as the Koopman operator learning frame. And eventually what we have is to use the learned operator to iterate it. And for a very sufficiently large K, and acting on the dictionary function so that we can have this uniform approximation of the U. And this is a summary using this diagram. And so the data just come from the data from the original ODE system. And we do this lifting because we have some observer, this test functions, and we do this transformation and learn this Zubov Koopman operator. And then we iterate it. And then we act on this identity operator, and then we can have this, approximation of the solution to the Zubov equation, right? And this part is very tricky because you probably have remembered that, let's recall this part, because we don't necessarily have the convergence of the, the Lipschitz constant, right? And even though we have a uniform convergence, we don't have the convergence of the derivative. And this part is to say that we can also do an extra layer of approximation of the approximator. And then it's based on some tanh, like a hyperbolic tangent function, right? And it just works like a straightening this high frequency mode into some very smooth mode, so that we can have this derivative also convergent to the, the derivative of the real solution, right? So we have some quick examples, and the first one is a demonstrating example using the first dimension, using a one-dimensional system. And we have even the analytical result of the EU here. And using this Zubov Koopman operator, we can do the same thing. And this is the eigenvalue and the eigenvector of the Zubov Koopman operator. And we have this top eigenvalue to be 0. And this is the evolution of, using this iterative methods, right? We start with this function, and after many iterations, and everything converges to the real solution, which is, pretty much after the iteration number 10. And then for the 2D polynomial system, we use this, this equation, and everything just makes sense, and the approximation is pretty good. Of course, for nonlinear, non-polynomial system like this two machine power system, and the boundary here is when we have the estimation for the uniform convergence. But I think you have remembered that this may not be readily be a Lyapunov function, right? We have to take extra layer of using the neural network to smoothen this result, and then we have to verify the boundary and the verified result is given here. And compared to the very benchmark tools, sum of square is much of an improvement. And the one thing to be noticed that this sum of square only have the ability to predict the region of attraction for known system, but even we have unknown system using the data, we have a better performance here. And here's another two system like a Steve system, and we can set this mu to be very large, so that we can observe some stiffness of the system, and using the numerical solver of the ODE, there some oscillations and stuff. And you can observe eventually there's going to be a very big sharp turn here on the boundary of the domain of attraction, but still the method is pretty good estimation and prediction of the boundary of the domain of attraction. So here comes to the summary and future work. So we have done pretty much at the same time for all of this work, starting from the model-based analysis for known system, and we have the physics informed the neural network construction of the Lyapunov function, and also the optimal control paper. And then we have proof that for a simple system, and we can even just use one layer of an extreme learning machine to approximate the Lyapunov function, which is pretty fast for low-dimensional systems. And the last one, and the fourth one is the toolbox. It's open source, and we have submitted last year to the HSCC. And the last paper is what I've mentioned about the Zubov-Koopman operator, but this just for unknown systems. Right? Everything just work by the same philosophy that we want to solve the Zubov equation, but using different methods, right? So here's some other work accepted by the last year NeurIPS, and they proposed this transformer approach, and claim that they work better for than the other tools. But there is a tricky part, right? And they have assumed the very specific form of this V, and then they sample the data and etc. to do the verification. But this reduce the many amount of the space, truncate many other possibility of the Lyapunov function. So yeah, so probably they can claim that they work better for this type of Lyapunov function, but not all of them, right? So here are some other type of work. So simply, if we can identify the system and we use the previous mentioned this physics informed neural network, we can still do the same thing. But this highly rely on the so the precision of the system identification, and we have many papers summarized in here. And especially for the last one, we have used the system ID methods and optimal control method using the solving the H-shape equation, right? And eventually we have observed the precision is much higher than the last generation of the benchmark tool. So a little bit of the future work, right? We have done the very basic verification of stability and of course the stabilization. How about the stability and safety together, right? And for example, we can solve the problem like rich, avoid, and stay, which is pretty much similar to the the stability with the safety constraint, right? So this type of problem is very tricky because sometimes the stability and the safety specification are conflict to each other, right? And doesn't guarantee that they can satisfy at the same time, especially when people are using something called the Lyapunov function. So it's sort of like they are pretty much just combine this Lyapunov and the Baire function together, but they overlooked some aspect that they cannot be combined on all of the domain, right? And we have to specify there is a maximal domain of the Lyapunov and the Baire function to exist. And of course, we want to solve this Lyapunov and the Baire function using the similar method by solving PDEs, right? And of course, this PDE is not easy to solve because we have an extra term of a constraint. And eventually, we can, extend out the work to some different topology, like a hybrid system, and we can construct the feedback law, et cetera, et cetera. Right, so here's some theoretical guarantee, and based on my PhD thesis, saying that, okay, these two functions can be combined, but only the existence of this combination of the function only exists on this open domain, right? And it's pretty much just the slice of the domain of traction, right? But just looking at this part, it's the same definition of the domain of traction, except we also want every solution to be safe and not touching this unsafe area, and for every time, starting from the origin, right? And we have proved that this set is open and forward invariant, and it's pretty much similar like a domain of traction, except that it's smaller, right? And the goal eventually is going to use this PDE method to figure out how large this is, and at the same time, we may have a chance to construct the Lyapunov the Baire function together, right? So here are some theoretical guarantees based on this paper, and we have some, applications to, stabilize and to stabilize the jet engine compressor for this surge control, and of course for some simple under-actuated system, we have an application to them. So here's the end of the talk, and thank you very much for your attention.